So now we are going to talk about MM1 systems, which means which means arrival time and service time are exponentially distributed, and there's one server. But the difference here is that we have a capacity on the system, which means we cannot have more than a certain number of people C in the system. For example, when C is 10, means we cannot have more than 10 people in the system, which includes the people waiting in line and people being served, all the people in the system. And when this is the case, once we reach the capacity, we will not accept any incoming arrivals. So they are said to be lost forever, lost to the system. All right, we won't be able to utilize the benefits we get from the arrivals, or we won't be able to serve them. The system becomes a closed system. And as soon as one customer leaves the system, it becomes open again. New arrivals can join. All right. And we will see sometimes the system never reaches its capacity because it's so efficient. The service rate is so small and the arrival rate is so large that the system never reaches its capacity. The call center example we learned about in birth death processes 2 lectures ago, that was a good example. The system was so efficient that the percentage of time or the fraction of time that new calls would be lost was so small. All right. Now, the first thing we're going to look at is the rate diagram. The rate diagram has changed a little bit, and the change is that previously MM1 would keep going here, but now it stops at C, which means a state of a system, which is the number of people in it, cannot go beyond C because we have a capacity, we have the cap for the system. So the difference here with the previous one, with the regular MM1, is that it stops here at C. But the rates are still lambda and mu. So again, we are interested in calculating pi's and L's and W's. Pi's are probabilities or fraction of time. System has a certain number of customers, and W and lambda are other characteristics, expected number of people, expected amount of time they spend in the system. So as you see, lambda, J is always lambda for J equals 0 to C minus 1. After that, lambda is 0. Lambda 0 itself is always 0. And mu 0 is always 0 because when there's no one in the system, we cannot serve anybody. And mu sub J is always mu for all the states from 1 to C. Okay. So one good thing about systems with capacity is that we can still have a steady state, or even if lambda is greater than or equal to mu. And which makes sense because the system will not blow up because there is a capacity for it and it cannot go beyond that capacity for it to blow up. Now let's derive the formula. So we're going to consider two cases. One, when lambda and mu are equal. So now you see that rho will be 1. And now because there is a capacity, it's okay for rho to be equal to 1. So in the first case, lambda and mu are the same. In that case, pi j is going to be 1 over C plus 1. What is C? Is the capacity of the system, 10, 9, 100,000, whatever it is. And L, expected number of people, is going to be C divided by 2. When lambda and mu are equal. What if they are not? If they're not equal, pi 0 is going to be 1 minus rho. This is what it used to be, divided by 1 minus P over C plus 1. Here you see that if C is infinite, because rho, and if rho is less than 1, that pi 0 formula becomes just 1 minus pi, the previous formula that we had. And then pi j, for j is equal to 1 to c, is going to be rho to the power of j times pi 0, pi 0. This is the formula that we had for regular MM1. And after that, for greater j's, it's 0, which means the probability that when you have a capacity of C in the system, the probability that you have more than that number in the system is 0, which makes sense. And then your L is going to be that weird looking formula here that I already copied in your skeletal outline. And you just have to write it down or memorize it and then use it. But regardless of the relationship between lambda and mu, W is going to always be L over lambda times 1 minus pi sub c. Pi sub c is fraction of time that the system is full. And W sub k, expected amount of time people spend in line, is L sub q divided by lambda times 1 minus pi sub c. What is LQ itself? It's L minus LS. What is LS? We learned that LS is when we have one server, it's just 1 times sum of these pi's, which is again 1 minus pi 0. Okay, let's look at an example. A one-man barber shop has a total of 10 seats. Inter-arrival times are exponentially distributed, and an average of 20 prospective customers arrive each hour at the shop. So that's my lambda per hour. Those customers who find the shop full do not enter. So there is a capacity. This is MM1 cap, MM1C. The barber takes an average of 12 minutes to cut each customer's hair. Because the previous one was in hours, so 60 divided by 12, so my mu is going to be 6. And as you can see, lambda over mu is greater than 1, which is okay because there is a capacity. Haircut times are exponentially distributed. So the system is MM1C, MM1 10. On the average, how many haircuts per hour will the barber complete? So my capacity is 10, lambda is 20, mu is 5, and questions B and C that I will answer in the next slide. So on average, how many haircuts per hour the barber is going to complete? Or what is mu basically? And then on the average, how much time will be spent in the shop by a customer who enters? So that's just W, because it doesn't say waiting or being in service. That's general W. For that, I need to calculate L and then divide it by lambda times 1 minus pi sub c, the formula that we had. So for that, I need L. Because L and lambda are not the same, I need to use this formula, the weird looking formula. And from there, I also know that pi sub j is rho j times pi 0, because I need pi sub c to use that formula. So this part is missing, this part is also missing, right? I get that here, and I get that from that formula. But pi 0 itself is 1 minus rho divided by 1 minus rho to the power of c plus 1. C is 10. So pi rho to the power of 11. And there I get, once I get pi 0, I'll be able to calculate pi 10 using this formula. So pi sub 10 is 0.75, and L using that formula is 9.67. So that's the expected number of customers in the system. System is always, on average, not always, the system on average is almost full because the capacity is 10. So my W is going to be L divided by lambda, which is 20 times 1 minus pi sub 10, which is 1.93, almost 2 hours. So that's a very busy barbershop. So that's the summary of systems with a capacity. There is one other example that you're supposed to solve, and there are problem sets that I'll share with you. Please look at those, and then you will be able to take the test.